Hello everyone, my name is Rusun Mandal and today I will be presenting the paper Multi-Net Real-Time Joint Semantic Reasoning for Autonomous Driving by Marvin Techman and colleagues. This research addresses a key challenge in autonomous driving: how to efficiently and accurately interpret visual information in real time. Introduction. Autonomous driving systems rely heavily on visual perception. While many existing methods achieve high accuracy, they often do so at the cost of speed. For real-time driving, that trade-off is not acceptable. Every millisecond counts. Multi-net address says this by combining image classification, object detection, and semantic segmentation into a single streamlined model that can process an image in under 45 milliseconds. Now, I am going to tell about some of the motivation in this slide. The motivation behind multi-net is to achieve high performance without sacrificing speed. State-of-the-art models like ResNet are, are accurate but computationally heavy. In self-driving system, we cannot afford that delay. Multinet uses a shared network backbone to carry out three different tasks simultaneously, allowing for reduced computation time without compromising much on accuracy. This makes it highly suitable for real-time deployment. Now, cures. I'm not sure what's more complex, the code or my robot's personality. Hope this code's liked by everyone. Here, some of the significance I want to discuss in this slide. MultiNet is the first model to combine classification, detection and segmentation into one real-time framework. It outperforms existing models like faster CNN on standard benchmarks like KITTI. It achieves about 23 frames per second, making it deployable in real-time system. Also, by eliminating complex components like proposal networks, it reduces architectural overhead and easier to implement and maintain. Now, I want to describe about methodology overview. Multinet architecture consists of one shared encoder, either BGG16 or ResNet, and three task-specific decoders. Each decoder is trained using a dedicated loss function, but they all rely on features extracted by the shared encoder. This joint learning strategy improves features representation and efficiency across tasks, allowing the system to process input images in parallel without duplication. Now, I am going to tell about methodology architecture. Here is the architecture diagram from the paper. It highlights how the CNN encoder fits into three separate heads. The classification decoder uses fully connected layers and softmax. The detection decoder uses ROL align and a bounding box regressor. The segmentation decoder is a fully convolutional network with skip connection. This setup allows the model to make joint prediction from a single image input, saving time in computational architecture. Here in figure we can see that contaminated features go through delta prediction and then prediction reverts back to it, and there is also we can see bottleneck, and we can see CNN encoder feature scale 2 encoding features, etc. And then classification decoder bottleneck fetch with software max and predict and make prediction. Now segmentation decoder also works in scale 1, scale 2 and scale 3. Now I want to tell about the experimental setup in this slide. The model was evaluated on the KITTI benchmark, focusing on three main tasks: road segmentation, object detection, and scene classification. The evaluation used metrics like max F1 and average precision AP for detection and segmentation and standard accuracy, and recall for classification. Images up to 1248 into 384 were used during training and interference. Now, I want to tell about result segmentation in this slide. Multinet using ResNet 101 achieved an impressive max F1 score of 96.29% in road segmentation. It beat all other models on the KITTI benchmark at the time of publication. What's more, it maintained better speed than deeper segmentation models, proving that it's both efficient and effective. Here we can say result segmentation in the figure. Now, I want to tell about the result detection. For object detection, Multinet achieved 89.79% AP using ResNet 101, wells ahead of faster RCNNS 78.42%. Thanks to roll align, the model supports scale invariant detection without requiring region proposals. It can run in real time at about 24 to 26 Fps with ResNet 50, making it highly suitable for deployment. Here we can see in the figure, there is clearly shown in the figure. Now I want to tell about the result classification in this slide. Multinet classification module achieved 99.84% accuracy and 100% recall. This high accuracy helps the system understand the driving scene and support the segmentation and detection components. The classification decoder performs robustly even across different road types, ensuring context-aware driving. Here you can see results in the figure. Now, some of the multi-net strengths include extremely fast inference under 45 milliseconds, high accuracy on all tasks, a simplified architecture with no external proposal generation, fully end-to-end trainable and publicly available for reproducibility. These attributes make it an excellent candidate for real-time autonomous driving application. However, there are some limitations. Multinet was primarily trained and tested on KITTI, which has limited environmental diversity. Performance drops slightly with deeper models like ResNet 101. It doesn't explicitly handle adverse conditions like nighttime or rainy weather. It focuses on semantic segmentation, not instant segmentation, which can limit its use in dense traffic scenarios. To summarize, Multinet is a unified real-time solution that handles three essential perception tasking using a shared architecture. It delivers performance that rivals or exceeds state-of-the-art models while simplifying the deployment pipeline. This model represents a major step towards safer, more efficient autonomous driving system. Here are some of the future work in the related research paper. Thank you.